Hey, well, good morning, everyone. It is our pleasure to host Alberto Akumazzi, who hails from Harvard-Smithsonian Center for Astrophysics, and will be telling us about case study, the ADS system. And just to give a little bio for him, so Alberto received his doctorate from the University of Milan. He has been working at Harvard-Smithsonian Center for Astrophysics since the late 80s, first in computer vision approaches, and then in 94 moving to the astrophysics data system, where he has continued to help run the show, in fact becoming a program manager in 2007 and actually the principal investigator since 2015. So Dr. Akamatsu is a world expert in scholarly systems, especially as it relates to other scientific publications and all sorts of bibliography systems. So it's our pleasure to have him here with us. Let me just give a reminder that please, if you want to ask questions, raise your hand and I will deliver this mic to you. And then please wait for the mic before asking the actual question. So Alberto, please take it away.
Thank you. Thank you. Thank you very much. Thank you, John, for the introduction and everybody for inviting me over. It's exciting to be here. I had heard about CLSP, but I never had the opportunity to visit. And thank you for making this such an interesting visit. So I was excited. First of all, this is a talk about the astrophysics data system, which is a database that astronomers use every day. But I have made no assumption about the depth of knowledge in astronomy of any people here. So hopefully everybody can follow it. And I invite people to ask questions while I give my talk, if appropriate, because I put together a lot of things that I thought might be interesting to this group of people. But obviously I did not have time to go into details on any one of them, but I'm more than happy to elaborate as I go along. So don't be shy. So as a way of introduction, let me briefly tell you what the astrophysics data system is, if you're not an astronomer. Is a project funded by NASA since the early 90s, as I mentioned. The main way in which is used today is that astronomers come to it and to search the astronomy literature. As of 2022, we have expanded the coverage of the disciplines that are indexed in our system to add planetary science and heliophysics. And more recently, we are adding other disciplines important to NASA. I'll tell you in a moment what that project is called. So it is, if you want to look for a parallel, it's something similar to PubMed for medicine and biological sciences. But we tried to do more than just index the literature, because otherwise you would be using Google Scholar or Semantic Scholar. One of the goals of our system is to interconnect resources, software, and data sets with the literature. And of course, we're service-oriented. We use any appropriate technology to deliver the content and functionality to our users. So in this presentation, I will try to talk about the system as a whole as an information system rather than something specific to astronomy and how to make it more useful for astronomers. Why is ADS being used so much? I think the primary reasons is that there's a lot of trust in the community in terms of what they find in our system. It's popular and trusted because we apply editorial policies in terms of selecting the content that goes in. And this is a recent survey of astronomers. As you can see, most people who use ADS are highly likely to recommend it to other colleagues. We, as I mentioned, are a system that stresses open access and open science in general. So we try to facilitate not just the discovery of publications, but also their reuse and linking the publications with other databases. Here I'm showing how astronomical objects and links to other databases are highlighted in our interface. We also index software records. So software that is cited in the literature gets indexed in our system and linked to the relevant papers through a couple of different methods. And of course, as a system that specializes in particular disciplines, we have implemented semantic search in different using search technologies. So we try to incorporate the relevant semantics and taxonomies that are important to those disciplines. I will talk about the search capabilities of our system, which have been developed, over time and where, they stand today. But first, let me explain what transition we're undergoing at the moment. And actually, the person most responsible for this transition is sitting in the room, is Josh Peak. ADS is a system, as I mentioned, has been used since the 90s by astronomers, but in 2019 or 18, there was a meeting where all the NASA repositories got together and tried to brainstorm about how to support open science initiatives. And one of the ways in which these people and data managers identified as a way to promote open science was to create a single portal for the literature spanning across all the science disciplines that NASA covers. So the goal here is to increase transparency in the way science is done, and having a single portal that indexes all the literature was one of the ways in which to do this. SMD here stands for the Science Mission Directorate, which is the NASA science component. So in 2022, a proposal was approved for funding this expansion. And in addition to the space disciplines that I mentioned, astronomy, so astrophysics, planetary science, and heliophysics, they asked us to also include earth science and biological and physical sciences. So since then, we started developing not just increasing the content in our system, but also thinking about new methods to make this system more usable, more effective for people working in disciplines that are fairly detached from astronomy, so the earth scientists and the biological and physical scientists. And so we are developing a new portal, and we named it the NASA Science Explorer. It's no longer astrophysics only. So if you're an astronomer, you can still go to the Astrophysics Data System. If you're an earth scientist, you will go to the NASA Science Explorer. They both rely on the same technology and database, but you will have different views and user experiences depending on where you go. So the way in which we present the NASA Science Explorer is that it's a literature-based open digital information system unifying all the disciplines that NASA cares about. We also restructured our team. So this was also a fairly involved transition in terms of how we manage the personnel inside of our team and the group of people working together. As you can see, there's a team of developers, a team of curators, and then scientists, which are subject matter experts in the disciplines that we cover. And this is a plot from the proposal, and one of the reasons that I think captures the importance of what we're doing. Here I'm comparing the acknowledgements found in the literature for some of NASA's most successful programs. You recognize the Hubble Space Telescope, where the data is stored here at the Space Telescope Science Institute. Chandra is the equivalent X-ray telescope, which is hosted at the CFA. And the other plot points there are the acknowledgement to the Astrophysics Data System. So that's obviously a much smaller project, but the impact and as measured by acknowledgement in the literature is just as great as these flagship missions that NASA is funding. So if you want to try out our new portal, you can go to sciexplorer.org at any point. And I'm building up a case for the technology used behind what we're doing here. you may ask yourself, again, why do we need such a specialized system for doing things that are readily done by searching the web or going to Google Scholar? So here I'm showing that we not only index the literature, strictly the refereed literature or even archive, but we include content that is work in progress and what we call the gray literature, so things that are not traditional journal articles. As you can see, there's a long tail of things that enter the system, including things such as observing proposals, proceedings, software packages, and high-level data sets. So these are things that you wouldn't find elsewhere. Here I'm showing a new feature that is being designed specifically for planetary science, where we index the literature using a taxonomy for planetary feature names. In this case, we index craters and other planetary features so that you can actually disambiguate the use of all these different names. Planetary names are tricky because they are names of people that have been assigned to specific features on different planets. And so you may have a name like Cassini, which is both a spacecraft and a crater on the moon and a crater on Mars. So disambiguation of concepts becomes very important. And also, as I mentioned, we link to data sets whenever possible. So we do this in multiple ways. One way to kind of kickstart this effort in the new disciplines that we're covering now is through text mining. So looking for links to repositories in the data availability sections of papers. But I'll show you later that there's also ways in which we integrate curated collections hosted and maintained by partnering organizations. And finally, we're developing specific features that will vary according to the discipline that you select. So a single portal will have a slightly different behavior and look depending on the discipline that you select in terms of what filters and what features become available to you. Yes, so the final piece of this is that NASA is funding us, as I mentioned, as part of a larger open science portfolio. So we are one of multiple initiatives that are being promoted in support of open science. And one of the goals is to make sort of common infrastructure available to all of these projects. And that's kind of the area in terms of machine learning and AI that we are interested in collaborating with. Why is this relevant to you? So one of the things that we put in the proposal, and we really, I think, not just sounded good, but we meant it, is that we can only really do this and scale up at the size of the database that we need to build by using machine learning, computer-based language understanding, basically. So all the capabilities that we aim to build are predicated upon our ability to use these techniques in the creation of the database, in ingesting and indexing of the data, and also in maintaining our platform in a state of continuous improvement. So it's not just about build it and then it will run itself, but we need to be able to retain the talent and the capabilities to innovate over time.
So how is the indexing done now? It seems impossible to take on something like this without either a large staff or AI.
So are you talking about physically how we get the data in the system, or what system are we using to index the data sets?
When I say indexing, just to be clear, I meant the semantic indexing that you talked about before, which enabled, like, there's a lot of library science going on here. Who's doing it?
Yeah. So we started using, I will show some of this in a moment, but we use an open source system called Apache Solr. I'm sure you're familiar with it. The sort of semantic part of it is implemented using a customized system for accounting for synonyms and acronyms expansion. So it's the traditional information retrieval model where you do query expansion and re-ranking. And we also have tweaked the grammar and re-ranking of that system.
So it's all based on terms rather than on, say, contextual embeddings of those terms.
That's correct.
Great, thanks.
So I'm keenly aware of the fact that technology is moving very fast, and using embeddings is probably in our future, but it's a large ship to steer in terms of how we will be able to do that. But that's one of the reasons why we're talking to collaborators and exploring other technologies. One point I wanted to make is that it may be of interest to you. I know some people already use the ADS in our API, but most of the things that we've indexed in our system are also openly accessible through the API. The only exception is copyrighted material that we are allowed to index in the system, but not redistribute through the API. And there are some ways in which portions of this may be made available as data dumps to collaborators upon request. So yes, SciX or ADS, I'm going to use this term a little bit interchangeably. ADS is the project, SciX is the product for non-astronomers, let's say. Can be seen as a digital library platform for data science, as well as for in-depth disciplinary research. I will get to, thanks for the question, to some of the features in the search engine. We obviously track citations, and we've incorporated that citation indexing in the search engine itself. We also are using anonymized usage to leverage that for recommendations. And we've also built things such as these visualizations. Everything that you see in the screenshots here is generated from our website, which is, well, there's two versions of it, but basically it's a single page application, JavaScript application. So everything that has been done on the website is something that could be done by any of you just by using the API. So that's the other thing that this says allowed is for other partners to integrate some of the results or metrics that we generate into their own systems. This is an example of the dashboard that an organization, an astronomy organization called NORAD Lab is doing to track their bibliographies. So this is pulling data live from our API. They generated a collection of papers about their different projects. And the metrics associated with these are updated daily as we update the system. And so they are able to simply incorporate that whenever somebody loads the page. So there's multiple ways in which our data gets reused and incorporated into other products. And the other thing, as I mentioned, is that we've only been able to do this because we have longstanding relationships with actually the suppliers of the data. So we have agreements with publishers that allow us to obtain their full text for the purpose of providing these services. And that's actually an important aspect of all of this because we wouldn't be able to allow for the sort of deep discovery of full text searching without having agreements with the different publishers. That's an effort that's not to be underestimated because it takes a long time and it takes a lot of negotiation to reach. So as of today, as you can see, we have about 9 million full text documents indexed in our system. All of these are full text provided by the publisher or digitized by our project. So there are things to which we have access to, our search engine has access to. And also we have scientists on staff, but typically these are projects that we do with collaborators. We work together with people interested in doing bibliometric studies or any type of sociology studies that use our data sets. Here's a study by our colleague, Michael Kurtz, our project scientist, Michael Kurtz, who did an analysis of open access adoption in different areas and subdisciplines of astronomy. Okay, there was a question about the search engine. So as I mentioned, we used an open source package called Apache Solar. It's built on a library called Lucene, which is also used by Elasticsearch. Many of you, I'm sure, are familiar with it. So the way in which you use Solar is that you can have fielded searches or unfielded searches, and you have to define a schema and mechanism for how you map one into the others. So here's an example of a very brief search. This is unfielded, so I'm saying I want to look for these terms anywhere in the database. And I'm on the right, I'm showing how that search gets translated by the parser before being executed by the search engine, to give you a sense of all the things that go on behind the hood. First of all, what gets typed by the user could be a topical search, or it could be an author search, it could be a date range search. So all these things need to be properly parsed and recomposed in subfielded components. And this is where the synonymic expansion, acronym expansion, and customized scoring takes place. So we did all of this by essentially develop the parsing, different parsing grammar for the searches that we support. I'll show you in which ways this is different from the traditional Solar parser. We took into account matching of author names due to transliteration issues and Unicode and whatnot. Other things, I mentioned the acronyms and all of that. The relevance scoring has been modified. So relevant papers are not only papers that have a good textual match to the input query, but also they're ranked, also taking into account the citation and usage statistics. And this is something that we tweaked over time in order to provide what astronomers consider the most relevant results. And we've incorporated, as I mentioned, the citation graph in the search engine for doing joint queries. So you can, I'll show you some examples of how you can search for papers on a particular topic, but also then apply, get results linked to them through the citation graph. Okay, so some basic examples are these. Here, the first one, I'm doing a full text search. So find the phrase exoplanet atmospheres anywhere in the full text of all the articles ever published in our system. The second one shows a search of the literature for articles that contain data sets that are labeled as part of the Chandra or XMM or MAST bibliography. The third one shows an affiliation search. There's multiple ways to search affiliations. We have normalized ways for institutions. This is just a generic search for affiliations, either at the Center for Astrophysics or Harvard University. We also integrate with the ORCID system, which is a unique author disambiguation system in our database, and we have plans to expand that to have full-blown author profiles in the next few years. And you can also search in the acknowledgement section. So this becomes important when you search for funding information or to see what funding, what institutions get acknowledged in scientific papers. So in this case, I'm looking for papers where the author is affiliated with NASA or where NASA is acknowledged. And the result is basically papers which are funded by NASA, either through grants or payment of employees. So the second order operators that I alluded to, these are something that was originally envisioned by our project scientist, Mike Kurtz, and it was implemented in our early search engine, which was custom built and developed. But I think this is something that is unique to our system as far as I know. They're based on the premise that the search engine supports any number of queries. So let's call these first order queries, where what's input is then matched against a set of documents, and a rank list is generated and shown to the user. The second order operators are functions that wrap the first order query in order to perform a second step, which takes into as input the list of papers generated by the first set. So if you can think of it, one way to think about this is that the second order operator takes a set of results, acts upon the set of results, and generates another list for you. There's 4 of these that are worth discussing. There's actually a few more, but these are the ones that are most useful to the end user, and I'll give you some examples of each one of them. The diagram here shows how each one acts on the first order query. So similar uses text similarity to produce results. Reviews look at citations to return papers that review a particular topic. Useful looks at cited literature to do the equivalent functionality. And trending uses usage data to show papers that are trending on a particular topic. So the easiest way to explain the similar operator is to look at what happens when you have a single paper. When you have a single paper, such as this, Astrolama paper, authored by some people in this room, you have a title, a list of authors, and an abstract. So if you want to find papers that are similar to this, the way we implemented it is sample the abstract, the words in the abstract, find the most relevant in statistical term set of terms that appear there, and then search the database for those terms and return the list of papers that have the highest similarity to those terms. So that's fairly straightforward and understandable. So if you click on that, if you click on the button that, I thought I was highlighting, the similar paper button, you end up applying this operator to the original query, which is just the query for the paper itself. And you find a lot of papers that are similar to it. As you can see, the papers you get back are either about Astrolama itself or any variation of Llama and other language models. So what happens if you take it one step further? Apologies for picking on Joe for this example, but I needed someone in the room and someone whose name was not ambiguous. So here I'm looking at an author list. This is how people generate lists of papers by a particular researcher. So now that I have all of her papers, I can apply the similar operator, and this will take the list of all the papers she's written, again, sample the abstract, compose a virtual, think about it as composing a virtual document containing all the abstract, descriptive abstracts, and then using that to generate a query. And this generates, obviously, a list of papers about Milky Way and Milky Way studies, which is what she specializes on. Because this is considered a single list of words and topics, one thing that gets lost here is the fact that she also works in other things such as NLP and CS. Again, this becomes a single unified query, so you get the most relevant papers according to this ensemble of all research papers. Okay. Other more interesting, I think, functionality are provided by the useful second order operator. And this acts in a somewhat similar, but also somewhat different way. What happens here is that we look at a list of papers, which are, again, the result of a first order query. In this case, I search for language model and knowledge graphs. And then Useful takes this list, looks at the cited literature in all of these papers, and ranks the literature based on how frequently each paper has been cited. The idea behind this is that if you want to find the important foundational papers that you need to read and understand to delve into a new topic like language model and knowledge graphs, this is what you would do. You look at the literature and it's a collated list, and then you find, for instance, all these foundational papers. Many of them are about the BERT model, Atom, and attention is all you need is also on this list further down. So again, this simplifies the need for people to scan the literature and just find this in a useful way and a very quick way. The opposite of this is what we call the reviews second order operator, which looks at citations to the papers that are generated by the first order list. And so what happens here is that when you generate a list of papers on a topic, you have a lot of variability in the list of results, and it would take a long time to read the entire list of papers. So one way to get people started on a topic is to use, to look at review papers on the topic itself. And the way this is done is calling or identifying the review papers as the ones that cite most of the literature in question. So again, following the same examples, if I say reviews of language model and knowledge graphs, I can find papers that have been written. By the way, most of the CS papers in ADS, in fact, virtually all of them come from archives. So we only have, this is not a very good example in the sense that ADS does not have a complete representation of CS literature in its database, but it does for astronomy and space sciences. So I chose these examples because I figured these are more relatable for this audience. So again, this is a good way to get a student started on a particular topic.
I had a general question about the second order operators.
Yeah.
Since you get an initial list and they operate on that, in your experience, which operators are, in what way are they dependent on the scores in the first round? Meaning, do I treat them just as a blank, unranked list, or should I take into account their relevance to whatever was the previous query? Any sense on how you deal with it and what would be ideal?
Yes. So we struggled a bit with this. There's two parts to this. One is that most of the second order operators, because of implementation limits, requires us to truncate that list. So there's the first query, the ranking on that query. The ranking determines basically what gets used and what gets lost, because you only take the first 200 records. And that ranking is this custom-built text similarity plus citations plus usage. The second aspect of it is that should the scoring of the first ranked list, as you say, influence the secondary papers that are attached to it. And we try to experiment with both. At the moment, we don't apply that, that scoring for reasons that I can't remember. I think we couldn't convince ourselves that this was providing any more relevant results. Having said that, most of the strategies we implemented were not, properly vetted using, training validation data sets for lack of resources, frankly. And so that is something that we may reconsider in the future. We have, related to this, we have plans also to, now that we have building a multidisciplinary database, to have rankings that are discipline specific, and that will get us back into this business. And in that case, we would we would use the knowledge of how relevant a paper is for a particular discipline to elevate it or boost it compared to other papers. Still allowing people to make that choice at search time, or being able to say, as an astronomer, what is the list of documents most relevant for this query versus as an earth scientist. So that is work in progress, and we have a plan for a base implementation, but then we will need, this time I would like to do some A/B testing to help us decide which way to go. Okay, the final aspect of this, I don't want to take all this time. We have the trending operators. The trending operators basically takes into account usage. So people who read this paper also read these other papers. You aggregate that to make essentially recommend papers on a topic that are highly read and highly connected through the usage network to the original list. In terms of personalization, the system supports creation of libraries. So these are collection of papers that are of interest to you. They can be personal or publicly shared. These are used to track research topics or compile bibliographies for a paper you're about to publish, and so on. You can also view each one of these collections in the context of a search. So there's a particular syntax that allows those papers that you put in a library to be viewed as a list of search results. And the interesting part here is that then you can use the additional search capabilities to act upon that original list. So the syntax gets a little complicated, but essentially I put this here to show that you can have your list of documents, that's the docs operator, and then you can say, okay, I've collected these papers that are interest to me, show me other papers that are similar to them, and by construction, this will exclude the original list. So you see things that are missing from your list, but which you might be interested in. And all of these things can be combined with date ranges. Here's an example of how I can search the system for documents similar to the ones I collected in my library, but that have been published in the last 7 days. So this is one way to keep up to date with what's being published that might be related to my interest. And this, because the syntax becomes quickly complicated and because people are busy, what we ended up doing is try to deploy this functionality as a set of notifications that people can subscribe to. You can generate alerts whenever papers of a particular topic are published or whenever people cite you. If you do that, you get an email notification that includes papers on a particular topic. And if you actually follow the links at the top of each query that is represented here, you can see the full list of results that are returned when that query is made. And as you can see, the query gets quite complicated, but you don't need to know it because all you did was implemented at one point as a query of topics I'm interested in, and then our system will generate the proper syntax to provide this information to you. So this is an example of how we try to remove the complexity from the search syntax and just provide the functionality directly to the user. The other ways in which our system becomes useful to research astronomers is that, as I mentioned, we integrate collections that are useful to the community, and we have 2 ways to do this. We have data connections and we have bibliographic groups that are of interest to the community. Oh, here I'm showing, for instance, for the papers that contain the mentioned JWST, there is a list of data tags. Those are archives and systems that have data sets associated with the papers in this list. And then bibliographic groups are also represented. You see that JWST and HST are some of the bibliographic groups with the highest frequency that appear on this list. The collections can also be curated by librarians, so people in the community can curate these using fancy pipelines and methodologies like what MAST is doing, or by simple human curation. So you can have a person be in charge of maintaining the bibliography, for example, of SETI, the Search for Extraterrestrial Intelligence, which is a group effort, and a bibliography gets created as an ADS library, and that this gets indexed in our system to generate that bibliographic group. Okay, so now I just switch topic to talk about how our system and our operation are based on collaboration, but also trust built on the community. And when I say community, I talk about both the researchers and the publishers. So we're trusted by the community because we vet all the content that goes into the system, and one requirement in order for us to do our job is to have access to the scholarly content that goes into our system. Other databases like the different archives, Simbed and NED, which these are projects at Caltech and in France, use that same content to generate databases and databases of measurements in astronomy. So this has led to a flourishing of digital libraries and archives that use the source literature as input to their goals. So one question is, do we have what we want? Is the system that we have today good enough for supporting research? And up until recently, most people would have said yes. However, with the introduction of AI agents and language models and more in general, all the technologies that we see now, I think there's been a disruption because we now have the capability of having expert assistant answer questions that were previously unable to be answered. So all of a sudden, the fact that this information is distributed in multiple archives becomes a barrier to having a single agent being able to reason and act upon a body of knowledge that, up until now was, well, that if it were locally available, could be more easy to exploit. So the plan now becomes more difficult because ideally we would like to be part of a community of archives that are able to collaborate and enable this more distributed reasoning over data, literature, and services that are spread across different archives. So I'll talk about some of the ideas that and plans that we have to enable that more broadly. Let me start by saying what we've done so far. A few years ago in 2021, we developed the first astronomy-focused language model. It's not a large language model, but we named it AstroBERT. This is using the BERT model developed by Google. And we then developed labeled data set to be able to fine-tune the model and use it for named entity recognition. So whenever we generate such data sets, to the extent that we can, we make them openly accessible so that other people can reuse those data sets or even use them for measuring, generating metrics on other language models. We also started using this model and other techniques to implement pipelines. The pipelines are useful for us are obviously what we use to ingest content and perform metadata enrichment as we ingest these data sets. And we're also started prototyping tools, leveraging large language models. I'll show you briefly in a moment what we've been doing so far. The philosophy behind this is that we don't want this to be just a one project focused effort. So our commitment is that when we create a data set or model, we're going to share with the community. So again, to the extent that we're able to, this goes on Hugging Face and is shared with everybody who's interested in promoting these technologies. And also when we create a tool based on these technologies, it's open to everyone. So it would be available through our API to anybody who's interested in using it. I don't want to spend a lot of time here, but AstroBird is no longer, it's a model of about 100 million parameters. And the interesting thing is that, it's only, it turns out that I was expecting AstroBird to be significantly better to the other versions of BERTs in some of the downstream tasks. These are tasks based on NER of named entity recognition for astronomy terms. And AstroBird is slightly better than all the other SciBERT and BERT, but it's not blowing them out of the water. So it starts making you wonder why, to what extent do we really need specialized models? And now that we have large language models, do we really need to fine-tune the heck out of them? Or are these models good enough for most purposes? The machine learning data sets that I mentioned, we have made them available. We created them as part of shared tasks for a workshop called Workshop on Information Extraction from Scientific Papers that was held in 2022 and 2023. The next one will be in 2025. Here's an example of labeled data, which is, again, named entity recognition using specific labels that are important for research in astronomy. So we're looking at telescopes, missions, wavelengths, and things like that. All of this is available on Hugging Face. Other labeled data sets that we used are the function of citations found in the astrophysics literature. So looking at the text surrounding a citation in the narrative of a paper, identifying which citations are given as background information or supporting statements supporting the argument being made in the paper. And finally, a proposed shared task for next year, I hope it will be something we call in the AstroBib pile. So this is labeled data sets that support the creation of bibliographies for data usage in scientific papers. And the question there is, can we use large language models or other techniques to identify which papers contain the explicit use of data sets, and if so, identify what those data sets are. In terms of how we use the technology, we have now a pipeline in production that, as I mentioned, is used to identify planetary feature names. This is just the screenshots for it. It basically has a multi-step process that uses some of the techniques that we mentioned, named entity recognition, identification of keywords, and then using a knowledge graph to evaluate how similar the extracted keywords are to the ones associated with particular feature names. And then we use now a three-pronged approach to use relevance, knowledge graph score, and answers from an LLM to decide whether a particular feature is, in fact, belongs to a particular solar system object or not. We also have developed an in-house system that features a chatbot plus embeddings. Unfortunately, this project was developed over a year ago. And the person who was the main driving force behind it has left our project. So it's been a bit stagnant, but it's something we would like to get back to. But this allowed us to experiment with the retrieval augmented generation, indexing of chunks of full text into embeddings, and trying to do an embedding search to support the RAG component, but also mixing the traditional ADS search as part of the retrieval, along with the generation from these search results. Okay. And one more recent project that we did with a student is a simpler issue. Basically, is facilitating the generation of queries. As I mentioned, we use Apache Solr, which means you need to learn the syntax of Apache Solr and then the extension that we made for it. And this sometimes is a limiting factor for busy astronomers who don't want to read documentation and so on. So this project was had the goal of finding creating a chatbot that would take a natural language query in input and produce the properly valid syntax for that equivalent query that can be sent to the ADS API. And we did it by basically creating some embeddings that would try to match a similar set of queries to the one input by the user, and then retrieving the corresponding Solr queries for that, and then generating it, giving it to an LLM to generate the proper query, and then carrying out the query itself. Okay, a few minutes left. These are the guiding principle behind all the things that we've been doing. I think it's useful to state them and be clear about them, because these are the arguments that you need to make to funding agencies and also data providers before you can ask them for anything. We want to have systems that are accurate, so we can't tolerate hallucinations in the context of scholarly publications, and it's obvious why we would do this. There's also concern about privacy. As you know, there's ways to get information leaked out of these models, and we need to obviously prevent that. And also, we need to respect whatever agreements we have with the data providers. It's not just about copyrights, but also it's allowed use. For instance, a lot of publishers are really concerned about having systems like our own start generating content that then may be all that a research needs. So the fear is that it's loss of control from a publisher who may be worried that a generative model would be enough for a researcher, and that person would no longer read their paper because our system would provide that same information. Two of the things that we're trying to do is, so when we talk to publishers, and again, we do this on behalf of the community, is asking them for specific permission to use their content in using language models. And my main argument is that if we don't have the reliable data, the vetted data from the publishers, then everybody falls back on what's scraped from the web or archive, archive is great, but it's not complete. And also the quality of the text that you can extract is not always great. So I'm pleased to say that one of the results from these conversations that the American Astronomical Society agreed to this arrangement, and we're now negotiating with other publishers to allow us to do this. So in this case, the text can be used for generative purposes in training models. The other proposal has been with extending this so that we can share this content with what we call trusted partners, who are groups that want to also advance the use of science and scientific results. So in this case, a trusted partner, i.e. your project, your institution, would ask for ADS to be a broker in redistributing publisher content for a specific purpose. And we would be the clearinghouse to provide that content to you. And again, this is work in progress, but at least one society has agreed to do that and will allow us. Text and data mining, sorry. So it's the experiments that you want to do, and again, this has become a bottleneck to a lot of students and projects being able to do interesting projects. Okay.
First question.
All right, thanks for a nice talk. So you mentioned the SciEx Explorer has expanded to different disciplines like earth science and biology. So I'm wondering what are the challenges when in semantic search when you go across disciplines? For example, are similar concepts expressed differently? And how do you deal with that?
Yes, so that is our biggest challenge. With, as we can imagine, with a larger corpus, the problem with ambiguity in the way concepts are expressed. I mean, you see this most prominently in the use of acronyms. The same acronym means one thing and what it's doing the other. So all of a sudden, you know, you're searching for HDF or wind, and it looks two things to heliophysicists and earth scientists. That's not a problem that we solve. There are a few things that we can do now with the existing search infrastructure to make that better. One is, again, have this discipline customized search experience. So you could see how acronym expansion is discipline specific. And so if you type HDF in earth science, it will get expanded one way. And in another discipline in a different way. But I think it's clear to me that probably the best way to go is to have use embeddings where semantics are kind of built into that infrastructure rather than use the traditional methods of having two different mediate at retrieval time. The last thing I will say is that I have this idea, but we haven't been able to work on it, which is to do better, explore the ability to understand the search intent at query time based on what we know about the user. And so we could do a first level of concept disambiguation and name identity recognition at search time. That's part of the goal of having this chatbot-like assistant formulate the proper query, not just in the proper syntax, but also with additional constraints about the discipline which is being used.
While we're potentially waiting for other questions, I actually have one. So you mentioned that the AstroBert results were modest, and it kind of begs the question about what the role of maybe domain specialized LLMs should be. So I guess, yeah, what are your thoughts on that? Like, do you see it integrating? Do you see other tools like fine-tune language models integrating into this kind of system?
So, okay, so if you asked me that question 3 years ago, I would have said, oh, of course we need specialized language models, and that's why we need AstroBert, right? Like, it understands the jargon that we use in astronomy. It's not that I changed my mind, but you know, I showed you the results of AstroBert. Actually, depending on the task, you can do better with AstroBert if you have a more sophisticated pipeline that uses other things on top of the language model. So it just keeps you honest about what that effort is. So then with large language model, I would have said, you know, if you asked me a year ago, I said, well, of course we need to fine tune the language model, right? Large language model because of reasons. But I believe that the jury's still out there whether the results are significantly better with the fine-tuned model. So I am mostly puzzled, but maybe it means that that's not where we need to put so much of our energy. And also there's a cost associated with any of this, right? Like we can't do our large language model anymore. So we can fine-tune it. Is that where most of our efforts should go? I'm hoping that the answer to the question comes from projects like University BD and all the other collaborators. So like there's a coalition of people interested enough to generate these models. The really important thing is that like having good metrics to evaluate how well they do, and then we're off to the race, because I think I see ourselves as mostly users of. We want to facilitate all of this, but we don't have the bandwidth to be the developers of or fine tuners anymore.
Yeah. No, that makes a lot of sense. And I'm curious, maybe if like some of these things that you described, like second order operations that could be done could be substituted with maybe lighter weight language models and re-ranking, whatever, these kinds of things that.
Yeah, 100%. So yeah, so what we have is an information retrieval system informed by technology that was commonplace 10 plus years ago. So with the language models of today, there's clearly an opportunity to overhaul the entire system. It's not something that we would take lightly or do overnight, but that's certainly something we need to pay attention to. And as I mentioned, it's a big shift to steer. If you don't think that.
Thank you.
I will admit that this is a comment and not a question, but maybe Alberto, you can add some things. I kind of want to just pitch the room, all of you here, that one of the interesting things about astronomy and that is hinged by ADS is that we have an extraordinarily rich system, mostly ADS, that connects our literature to the raw data and also to the code and to the images. All those things are very richly connected. They are sometimes hand curated, they're sometimes, technically curated, and that makes it a really interesting system for thinking about the connection between language, scientific discovery, data. And that's one of the things that has, created the relationship between Space Telescope Science Institute up the street, where John and I and a few others work, which holds a lot of the data, ADS, and CLSP, which is hosting here. So just to put it in your minds, if you're ever thinking about these kinds of questions, how do we deal with multimodal data? How do we deal with these things? There's a huge open data set here of a pretty compact discipline whose data is all free and not dangerous and not a problem for anything, right? Galaxies don't mind if they are studied. So it's just we found this sort of rich seam here, and that's part of what John's program is this JSALT program is trying to explore. We've been working just with text, but it goes much deeper than that. So I don't know if you wanted to add anything to that overall pitch, but I think it's a great place for CS people to be involved.
So today, I was able to participate in one of your stand-up meetings, so heading in. It was interesting to see how it's broken down in three parts. There's data, there's retrieval, and there's generation. Right? So in terms of what our project does is like, we're certainly the place where we aggregate all the relevant data for the literature. So again, we do it for our own services and functionality, but we would like to share more of that with the community. The retrieval is what I described in the current search engine, and that also is a technology that is rapidly evolving. So we'd love to collaborate on that. And the generation is the next frontier for us. I think we need to wait a little bit till the hype curve gets back to the what's feasible and what's reasonable to do, because it takes also time for the relevant people to be convinced that this is not a harmful thing. So it's not just about technology, it's about sociology and research. Thanks. But I'm here hoping that, talking to so many clever people, we can find ways to collaborate. That'd be awesome.
So my question actually follows, Josh almost by plan set me up. A lot of the examples you gave throughout your talk were the kind of queries and exploration of a data set that you do in libraries, like it mostly focused on finding things in the literature. But you said very early on, ADS does have resources, including code and data. Do you have examples of what people look for in code or in data? And basically, I'm trying to understand the need a little bit better. I understand the need to search literature, but we do it all the time as scholars. But code and data, my go-to used to be Stack Exchange. Actually, it still is. I don't go to it, but yeah.
Yeah, thank you. I didn't have enough time to get into it, but so the disclaimer here is that one of the reasons why we started indexing high-level data products in India is basically to track it and link it to the literature. So we're not.
Okay, and I think this might be our last question, which is coming from Joe.
So thank you so much, Alberto. This was a wonderful talk. So kind of moving into the line of thought that the limits of my model are the limits of my data, which seems to be the case now, at least from my perspective. I really want to go back to what you're saying about the trust you're building between you and the publishers, and that you will work together to get some really nice data sets. And people, if I understood correctly, you can submit projects to NASA ADS. And I was wondering, just from your perspective, what are some projects that you think this will enable, and what are some things that you're deeply excited about for the future? Could be translation in other languages, or just want to see what flavors you have in mind.
Yeah. So
beyond the hour. So let's thank Dr. Akamatsu again. Lovely talk. Any thanks? And Sanjeev, do you want to say something about lunch?